Hey, hello, hello. Can you hear me? Okay, great. Before we start the talk, well, a quick introduction. I'm Simon. I run this conference. I'm a Lucene commuter.
I'm Robert Muir. I work on Lucene.
And we wanted to actually encourage you to ask questions during the talk and afterwards. And we bought 8 beers, and each person who asks a question gets a beer right away. So they're cold. Come on. When do you get your beer? No, it needs to be relevant to the topic, okay? Okay, good. Like Ryan has the beer here, and don't worry, Ryan doesn't drink beer, so you're good. You're good. Okay, let's go. Yeah, another quick introduction. I work for Elasticsearch, and Robert works for A9. You probably find us on Twitter. Those are the tags, and if you want to find us for in terms of like Lucene work, I think that should be easy. Just use Google. Oop. What's this?
We have technical difficulty. Sorry. Yeah. This is not good.
It's all empty?
PDF export.
Awesome.
Can we just run it from here?
Yeah, sure. Oops. Does this work? Okay. Yeah, okay. Cool. Hey, there's an agenda.
Sorry, guys.
We fixed it. Cool. So we're going to introduce first what we're going to talk about. There's a lot of talks that you usually see where people just dive in the topic and you don't know what they're talking about. So we try to introduce this here. So everybody uses Google, right? And one of my favorite features is the search as you type. So you type something and you get search results as well. This is not what we're going to talk about. Sometimes you mistype something, you get did you mean. This is not what we're going to talk about. What we're going to talk about is this up there. It's the query suggestion. You type something and you get a query suggested, which you eventually execute against the search engine. And this is something we spend a lot of time lately in Lucene to build software that is specialized for this case. And this is what we hopefully going to give you guys an idea today how this works and how you can make use of it. Okay, go on to the next slide. Okay, so what is the big deal here? The problem with search is that, well, on the one hand, it needs to be good in terms of quality, and on the other hand, it needs to be fast. But fast is a totally different story when we're talking about suggestions, right? First of all, you're getting a lot more queries, so you need to handle a lot more load. You need to surf super, super quickly. You better return your result instantly. Like less than 5 milliseconds is usually what you really want. If you look at the average search query, I've seen in my consulting life, it's about like 100 milliseconds, maybe 150, 200. This is not work with suggestions. This is too slow. And the user experience here is super important. If the suggestion comes for the first character while I'm done with typing, it's useless, right? So you need to be really quick here. So bottom line is, be super fast. This is the big problem domain here. What you essentially do is you fighting the speed of light. When you have a server sitting in Amsterdam and somebody from the US sends a request, like it types the first character, it goes all across the ocean and back, right? This is roughly about 10,000 kilometers, and the lower bound is 67 milliseconds here. That's the theory, right? You can easily double this, and this is like where it gets realistic. So the only real solution to this is, use Amazon Cloud or some other cloud and deploy worldwide. What you really want to, what you want to get when you want to deliver really, really good suggestions is something like 50 frames a second. This is like the frequency you want to get here. Yeah, we try to build something in Lucene that helps you to do this, that actually allows you to go there. But the software as its own, it doesn't bring you that far. You really need to think about what you want to deliver here. There's a couple of things I want to let you know, like what you really need to pay attention to when you build something like this. Especially the ranking. What makes a string a good suggestion? Why is Barcelona better than Berlin for the query B or something else, right? Why is this different? Why is this something you want to suggest rather than something else? So ranking here, you think is very domain specific. You want to filter trash. Like there might be misspellings in your data. You don't want to suggest something like this. You're probably going to retrieve something, but the results will be not really good, right? And on the other hand, it's very domain specific. But if you let's say you search for songs or bands, you type Who, you probably want to suggest The Who. It's probably going to be much better for your relevance eventually if the query is The Who, because it gets more context, the band. Or somebody types Captain US, you want to suggest Captain America, because this is probably what it is, right? Or you have Foo, whatever you want to pronounce this, like you mistyped F and G, and you want to suggest Foo Fighters, and everything is like uppercase written, and then it's not lowercase, and you want to basically apply fuzziness, analysis, synonyms, all this kind of stuff you want to do in your full-text search application as well. Here's a use case that actually uses the Lucene suggesters and the stuff we're going to talk about today as a very interesting feature. It's a SoundCloud website, and when you type something like Foo whatever, you get actually Foo Fighters suggested. Right? So it applies all these kind of analysis. But the interesting part about this is not actually a query at the end of the day. This is a navigation. So it's some kind of use suggestions as navigation. And a lot of websites have this kind of behavior where you just go and just type in a query and press the first result to get to a landing page. The interesting part here is that you can actually take a lot of traffic off your search engine by using suggestions as a direct navigation tool, right? This is something that is really interesting. But at the end of the day, SoundCloud also uses this as query suggestions. Can you go further? Here in the lower bar, you can go and try it out. It should be reasonably fast from here. This is the exact same thing what we're going to present today. How do you build something like this, roughly? The interesting part is for the navigation part at SoundCloud, there's more information coming back than just a string, right? There's highlighting information coming back, offsets. There is information about the actual suggestion. So each unique string points to an entity, and this allows you to actually point the user directly to the landing page, or even use this in your search engine, because at the end of the day, if you get a suggestion, you also want to, if somebody searches for a suggestion, you also want to present results. If you don't get results, that's kind of odd. Yeah, so some interesting facts I got from some SoundCloud people is that the suggest queries per second is roughly 3 times more than what they see on their search engine infrastructure, but there's more load than just from the web front end coming in here. And that suggestions actually improve search precision. Like if you get the user to type in what he actually meant, it's easier for you to give him a good result. The suggestions here are actually weighted with some interesting scheme Peter Bergen was talking about yesterday as well. It's similar to the search engine weighting. But I'm going to omit some details. Some of you have seen the talk yesterday about the SoundCloud search infrastructure. You can watch it on the video, and it's probably know about the more about the details. Benchmark-wise, these the suggesters. They're running roughly like 10,000 queries per second in the benchmark. They can do way more. This doesn't mean that they actually run at this rate at this point, but this is still what they can do in theory.
Hi, so this is another use case. I don't know if you're familiar with Yelp. It's very popular in the US. It's just a website you use to look up things like restaurants, get reviews, and it's very popular for, like, if I want to find something nearby, I want to go eat Thai food, then I would go to Yelp and find a good place with good reviews, look at the price, do some comparisons, and I'd see the location and know the times and everything like that. So they actually gave a talk at Lucene Revolution, I think 1 year ago, talking about how they wrote their suggester with Lucene, and it's open source on GitHub actually. But the interesting thing I thought that they have is their suggester is influenced by your location. So you have this idea that they may have many, many restaurants, but I don't care about restaurants in Berlin if I'm in the US. I want ones that are close to me. So how can we make the suggester, use this information? And what they do is they use geohashing, and they put their suggestions into their suggester multiple times with varying degrees of precision. And this allows them to basically maybe double or triple the size of their suggester, but who cares? Because now they have, auto-suggest, right? So this is an example, right? This is what a geohash looks like if you're not familiar with them. It's just a string that kind of represents that place. And as you take off characters, it becomes less precise. So maybe you have something like a city, county, state, and so that's essentially what they would put in their suggester, is they add these prefixes, and then when they go to run their queries, they do the exact same thing. And so you can kind of figure out how this would allow you to influence ranking based on location. I'd say I don't know, their exact formula, but I suspect it's a huge part of the suggester ranking, location. So I think that's a good example, but what can Lucene do in general? Like, what do we provide? Because they obviously have their code on GitHub that they built off of Lucene. Why did they decide to use Lucene's framework, and why did SoundCloud use it as well? And so the idea is to tell you kind of the features we provide. One word of warning about our suggester is it's kind of new stuff, and so it may not have the best API. In a lot of cases, the way to go about it is to take a suggester that's close to what you want and just take the code and modify it. It's open source. So eventually, I think we will have a good evolved API where we have, it's extensible and you have like a normal package you would use in Java, but currently, you may have to do some hacking. So, but what we give you, the main thing is the top N most relevant suggestions, right? So it's based on ranking, and it's efficient. So this is sort of like search, where the user wants top N results. We let you use the text analysis chain that you would use with Solr or Elasticsearch or Lucene. It's basically, Lucene has many analysis components already built to do things like remove stop words, remove accent marks, things like that. And so being able to reuse that for auto-suggest gives you a lot of power already, that you already know how to use. We can correct spelling. So that's the idea of, like the example from SoundCloud is the user may make a typo. And one way you can do that is with did you mean, but another way you can try to do it is to actually handle it in auto-suggest itself, too. So it's even better. As far as our implementation, this is optimized for a high-volume website. So it's not a toy. This is something where you build your suggester. It's kind of, you can think of it like a model, and you build it, and then it's totally immutable. And it's very fast. And it's essentially a byte array in RAM. So FST, what is this? Why do we care? Well, I'm not going to explain what it is. I'm just going to say why we care. And this is a nice blog post that went out this week from Aaron. He worked at Internet Archive. And what they have is they have a list of kind of every URL they've ever seen, because they take the Wayback Machine. What it does is allows you to look at old copies of web pages. So they're sort of archiving the internet. And they have somewhere on the order of hundreds of billions of these URLs. But instead of trying to build an FST of that, which would be many terabytes, they started with, well, let's just do all the host names that we have, right? This is something more reasonable, only a little over 1 billion. So they built this FST, and it shows you that it's only slightly bigger than if you were to gzip that list of host names, except you have the ability to do over 100,000 queries per second on this thing. So this is very powerful. It's small, it's efficient, and it's fast. So that's what we want for auto-suggest, and that's why we use it. So now we're going to talk about, we have a few suggesters to talk about, and it's kind of like a timeline. Like we started here in Lucene, and then we moved forward and advanced them, and so I'm going to kind of show you the timeline so you have the idea of all these suggesters are still there, so the simpler, earlier ones you can still use. But of course, I'll recommend we use the most recent one with all the greatest goodies. So we started with this one. It's called FST Suggester. This is a very simple one. The major weird thing about it is that you can only have 256 possible weights because the weight is a single byte. So you cannot really have fine-grained weighting, but other than that, it's very fast. And the way that it works is it puts the weight in front of the term in the data structure. So when we do lookup, we just do 256 lookups at most, and that's how we get results in ranked order. So extremely fast, no stuff like priority queues or any of that. But the disadvantage is, again, you don't really have good control over weights, and 256 values may not be enough to get the quality you need. So what we decided to do was, can we improve this, and give you a little bit better weighting? And we come out next with the weighted FST suggester. So this one is good because you can use 32 bits for your weights. That's the main advantage of it over the previous one. It's a little bit fancier in how it works, because what it does is it builds a weighted FST, so the weight is part of the data structure, and it can do a shortest path search, is what it does. So it walks your input, in this case WEA, and then does shortest pass from there. And so it gets the n shortest pass, and that's the n top n suggestions. So a little bit more complicated, more math, but more powerful. So one issue with that one is it's still not very good. It still has some limitations. For example, the matching is exact. But we would like for you to be able to maybe be insensitive to accent marks or even case. You may want to present the case in mixed case the way it's supposed to be, but still allow for case-insensitive correction and things like this. So what we decided to do is, can we use Lucene's analyzer chain, which already can do all these things, and plug it into Suggest? Because then this would give you something even more powerful, and you already know how to use it. So that's what we did. And so this is a crazy example. It's Japanese, but you actually cannot do auto-suggest for this language without having something like this set up, because it works on this completely different analyzed form that looks nothing like the text you see. Anyway, so the idea here is, if you want to remove some accents or something like that and still have it insensitive but show the original term, you can use analyzing suggester, and you just give it Lucene analyzer.
So there's a little story behind this. The latest and greatest, I would say, is the fuzzy suggester. And last week when we started preparing this talk, we were like, how are we going to visualize this? This is really complicated. And we figured out we can't. So we just put this up. Wet. What's going on? No, to give you actually a little bit of information about this, how this works, it's a suggester that is essentially an analyzing suggester. It's a subclass, a direct subclass. And it extends analyzing suggester by adding roughly about 15 lines of code, right? So it's just 15 lines of code more complex than analyzing suggester. But those 15 lines of code do actually a lot of things. It's based on a Levenstein automata. This is a data structure that we use for fuzzy searches in Lucene, since Lucene 4. Some of you might have heard about it. There's a lot of people have talked about it. Just the automata invasion in Lucene brought us several 1,000% in performance improvement for fuzzy search. And we figured that actually we can use the same technique to do suggestions as well. What we basically look at is there's two finite state machines, right? It's an automata that represents a prefix with and accepts all the terms that are within the Levenstein distance of 1 or 2 of this prefix. And we have an FST, which is our index here, essentially, that we want to suggest from. So we can intersect them. We can build another automata that accepts all the possible prefixes here. And this is what we do, and we extract the prefixes out of this intersection and build the top n based on them. It's basically, you can think of as you entering multiple prefix queries and use the letters you just typed and mutate them in a way that they accept all 11-side distances. Wait, but what is 11-side automata? Like, I want to really give you an idea why this is hard to visualize. This is 11-side automata for the term dog, so 11-side distance of 1. This is a very, very, very simple one, right? If you really look at production ones, there's no way that we could put this up here. But what essentially this is like when you think about the term dogs, D-O-G-S, right up there, this automata accepts all the terms that within 11 standard distances of one are dogs. And this is a really efficient data structure because this way we can use the power of the analyzing suggester, and due to the intersection, we can also fix the spelling errors on the fly. Speed. Speed is a big question here. Well, it turned out that they're still pretty fast. It's 10 times slower than the analyzing suggester, but as Mike McCandless said before we committed it, it's 10 times slower than crazy fast is still crazy fast, which is kind of true. But I want to get over to Robert and tell you why these suggesters are actually as fast as they are today. There's a funny story behind this.
Yeah, this actually is a funny story. So we had a benchmark for the suggesters from the very beginning, and we were working on suggesters. The benchmark actually had a bug. So we were working on this problem where can we correct spellings, and I thought, this is too slow. What we're trying to do is too slow. It's only 10 QPS. So it's a big, big problem. We would like, it's got to be at least, 25 QPS or something like that to be useful. We're doing these benchmarks. The bug in the benchmark was all of our suggesters in Lucene were 1,000 times faster than we thought they were because someone calculated it wrong. So that was a pretty cool day to figure that out and to say, oh, wait, 10 versus 25? Who cares? Because 10,000 QPS, right?
Even
we have
like
a question. We have a question here.
Oh, awesome.
A beer.
A beer. The question is, how long do we build? How long does it take to build the automata? You mean the Levenstein automata at query time? It depends.
Depends on the length of the word, and that's
depends on the length of the word, and it depends on how complex your analysis chain is. If you have a very complex query time analysis chain where you have synonyms and stop words and all this kind of stuff, and there's a command in the code that says how slow can this be. Actually, I don't know. Our recommendation is use a simple query analysis chain and do more work at indexing. Then you're pretty much at least 10,000 queries a second. So building the automata is usually pretty fast. Yeah. Did you get a beer?
Yeah, she got a beer.
Okay, very good. Go ahead.
So we use the same technology for the inverted index. The same like finite state machines that we're talking about here. They're used in various places. For example, the term dictionary. We store the terms this way actually, and we execute things like regular expression wildcard queries. We use the same technique here, but I guess the difference is that suggesters have to be much faster than the inverted index. So we do things a little bit differently. We load everything up in RAM and things like that. So it's kind of a little bit of a different story. It takes long. You think I'm going to spend 2 hours to build this suggester and use it for a couple days and then build another one and load it all up in RAM and serve. I don't want to have garbage collection. I don't want to have anything that would cause someone to have a 50 millisecond response time or something like that because their fingers are waiting. They type the key and they want stuff coming back fast. So yeah, we do things a little bit differently, sometimes a little more hacks, but in general it's the same. There's a lot of same code we use in the inverted index.
I want to add to this why suggesters are actually fast story a little bit. There was something going. Somebody added a feature, I think it was analyzing suggester, and the query benchmark dropped about like 5,000 queries a second, and we were like, this is a lot, right? Like going from 60,000 to 55,000. But it eventually turned out we tried so hard to get these 5,000 queries a second back, but it turned actually out it was 1,000 times more. So we actually spend so much time optimizing this code to get this 5,000 queries a second back. We would have never spent if we would know that it's actually not 50,000 but 500,000 or 5 million queries a second at that point. It's crazy. But yeah, that does, we get the good code from that. Some of it is kind of crazy, but yeah, what's in the pipeline?
So we described kind of where we are in Lucene, the different suggesters, kind of a timeline, and the latest one is fuzzy suggester, so that gives you all of the goodies. That's all the stuff we can do. But these are kind of limited to a few use cases of suggesters. Like the idea here is your suggestions are phrases, so you have this list of phrases, and maybe they're products or something like that, or maybe they're restaurants, or maybe they're songs and artists. But there's other use cases for suggest that we don't do well. And so one idea is that, that's called infix suggestions, and that's where the order of the words doesn't necessarily matter, right? So we want to correct someone if they put the words out of order. So it's kind of like a fuzzy correction, too. But this is there's different approaches for this. There's actually a Jira issue in Lucene. You can search for it. And there's 2 patches already with 2 different algorithms for it. So I think this will land in Lucene pretty soon. And then we have what we call predictive suggestions. So this is more sort of like Google. So if you have full text search, where you have a lot of users issuing queries that have never been issued before, you have this long tail, then how can you do that? How can you suggest something that's never been searched before? Well, the idea is that you're not trying to predict the whole suggestion. You're not trying to complete their entire search box. You're just going to try to complete the next word. And then they're going to keep typing, and you complete the next word after that. So something like this can work on like pairs of words. So given the previous word, I'm just going to guess and predict the next one they're going to type. And given that, you can suggest things that no one has ever searched before. But you can also suggest things that make no sense at all and maybe don't return any good results. So that's the downside.
Some recommendations, if you start really working on this, maybe one of the best recommendations or the most important recommendations, I think, is run this in a different piece of infrastructure. You will be hitting this service as much more traffic as your search engine will get. It'll also take off traffic of your search engine, but the request patterns are different. If you can easily think of this as it's the number of queries a second your search engine gets times the average string length, right? The average query length. If your average query length is like, I don't know, 15 characters, like you get 15 times more requests on your search engine, roughly. If you plan like this, then it should work quite fine. I suggest to use something that is non-blocking, some event-driven web server or something like this for that. This should probably give you a really good infrastructure here. Invest time in your weights. This is really, really important. It's not like like a search engine where you just trash your data and you do a search and it's doing reasonably well. You really need to think about what makes one string a better suggestion than another for a given prefix. Like when you think of restaurants, you probably want to use ratings, right, or some other factors that you want to put in there. Like how popular is a certain string? You can use click logs, but it's important that you think about this before you're doing this. Pruning the data, you probably have a lot of strings that will never be searched for. Right? Let's say you have a rating for restaurants where like the restaurants with the rating 0 and they have 100,000 clicks but have never got a good rating, you probably don't need to suggest them at all. So you can trash this. It helps you to reduce the build times, reduce the size of the FST. It helps you get better suggestions at the end of the day. Detecting bullshit is very important. This is something that I personally figured out that is super, super important. Imagine somebody types HTTP, and you're suggesting the hottest porn website. This is probably not good, because you're dealing with user input. Like somebody types in something in a forum and saves it in his profile, and you want to suggest on the profile, there's always trolls. So you want to detect this. This is something that comes out immediately. It's not like that you need to enter the entire relevant query, like a character is enough, right, to get something out. This is also why waiting is very important. Yep, there's a question. How do you detect bullshit? So there's a couple of techniques. What I've been using in production is classifying algorithms. Like you tag things that is typically coming in as spammy, and then pre-filter strings at a time. This is domain specific, but machine learning can help here. You can do easy things, regular expressions that match a URL, for instance. You know, if some username starts with HTTP : it's probably not a good username. You want to filter these kind of things. Yeah, this is a hard thing to do. It's certainly not easy. I mean, like all the pruning the data and the weights is not an easy task. But it's important that you think about it ahead of time. And simplify your query analyzer, as I said before, because it could cause very long automata build times. Yep. Questions?